All right, welcome back, Physics 12, to our last video on induction for the year. So I'm going to start out with a few just definitions. We kind of danced around the topic a bit, talked about the idea, but haven't really given these some formal names. So a couple of formal names I'm going to give you is one is something called magnetic flux linkage. So we know magnetic flux. We had a formula for magnetic flux in and of itself, which was B times A times cos theta. So flux linkage is essentially when you are linking together multiple loops. So in other words, we're looking at coils, multiple coils or solenoids. And so the formula is just the same as we had before, but we're kind of adding in the N. So where magnetic flux is BA cos theta, magnetic flux linkage is NBA cos theta. So just one new term for us, because it might come up in the video or in the questions. So another definition is Faraday's law of electromagnetic induction. We have seen this before, we've just given it a name. So this is just as a reminder as well, this is this formula here. Our EMF, so this is EMF, which is also known as potential difference, which is also known as voltage, equals negative N times delta phi, where phi is this flux. So there, flux equals this. So in other words, another way of saying this as well, just to backtrack, N phi equals flux linkage. Okay, so epsilon equals negative N delta phi, or the change in flux linkage, divided by delta time, or just divided by time. Either one of those is fine. So this is also written as negative NBA divided by T. Okay, so this is what Faraday's law of electromagnetic induction is. It tells us how big that EMF is going to be. Now, last class we talked about Lenz's law. So we were specifically talking about, with Lenz's law, it was dealing with PD in a coil. So with Lenz's law, we always were referring to a coil, and this was the one where we said if we're getting, all of a sudden we have more flux going into a loop, then we need to create an EMF or a current which opposes that. So if we have more flux going down into the loop, we need to get the flux back out of the loop, and so we would need to, in this case, create a current going counterclockwise, because we know using our right-hand rule, a counterclockwise current here would produce flux going in this direction, and that would kind of cancel out the change. So Lenz's law says whenever there's a change in the flux going through a loop, we need to induce a current that will reverse that change. We're getting more downward flux, we need to get less downward flux, or more upward flux to cancel it. We're getting less downward flux, then we need to get more downward flux. So it's always producing a current to produce a change, which counteracts the initial change. Well, what happens if we just have a conducting bar? So this is not a loop. Can there be a potential difference across a bar if it's not part of the loop? And the answer is yes. Yes, you certainly can have a potential difference where one part of the bar has a higher potential than another part of the bar. And the best way that I can use to explain this is I want you to think about, let's say we have this bar right here. And in this bar, there's a series of positive or negative charges that are free to move. You can think of it, you can imagine it either way. So let's say we're looking at the positive charges. As this bar moves to the right, so there's not just this positive charge, this positive charge, this charge, all these positive charges that are in this loop right here, or in this bar. Now, as the whole bar moves to the right, that obviously means that this one's moving to the right, this positive charge is moving to the right, this one's moving to the right, etc. So every one of these charges is moving to the right. Now, if we have a positive charge that's moving to the right, and we've got a magnetic field that's acting into the page, what direction is the force going to be on that charge? So take a minute, think about which rules you might have learned that might help you with this. So you got a positive charge moving to the right in a magnetic field that's into the page. What direction is the force going to be on that individual charge that's moving to the right? So we need to pause the video to get your right-hand rule out by all means. Okay, so Well, let's do the right-hand rule for this one charge over here. Let's look at this single charge right here in the middle. Now this charge in the middle here is moving to the right, so that's going to be my index finger pointing to the right. Now the magnetic field is going into the page. We know this because of the X's that are listed here. X means it's going into the page, like looking at the back of an arrow as it flies away from you. So that's my three fingers are going to be pointed downwards into the page. And if my index finger's to the right, three fingers are down, what direction is my thumb? Well, my thumb is going to be upwards. So the force on these charges, positive charges, are going to want to go up towards the top of the bar. Now, for our negative charges, let's think about the electrons that are in here. So for our electrons that are in here, they're going to also be moving to the right. Now, for the negative charges, we would use our left-hand rule. And so again, index finger of my left hand going to the right, three fingers pointing downwards, and my thumb is pointing towards the bottom of the page. So my negative charges are going to want to go this way here. And so in fact, using our right hand rule and left hand rule, that's going to be for positive, negative charges. We know that there will be a PD will be produced, potential difference or an EMF. It'll be positive at the top and negative at the bottom. So it is creating this force. It's kind of forcing these charges apart. The positive ones all want to go to the top. The negative ones all want to go to the bottom. Now, hopefully you'll recognize as well, if there's a limit to this, right? So if I start piling a bunch of positive charges up here all together, and I start piling a bunch of negative charges all here down together, well, they're going to push against each other as well. So you've got these two competing forces. You've got this force from our right-hand rule that says the negative charges will want to go downwards, but we've also got the rule that says that negative charges will repel, and so these two forces are going to balance out. So it's not going to be an infinite amount of voltage, but there'll be somewhat of a positive voltage up here, somewhat of a negative voltage down here, but the charges will also repel each other. So it won't be an infinite amount, but there will be definitely some potential difference. There'll be more the positives will be more crammed together up here, the negatives will be more crammed together down here. Okay, so hopefully that makes sense. So what if we have a formula, or what if we have this conductor as part of a loop? And this is an example of what's used, for example, as a rail gun. So you can you can kind of, instead of having a resistor down here, you can have a potential, and that will result in this bar flying off to the right. So what we've got here is we have essentially a completed circuit. This is a wire here, this is a wire here, this is a wire here with a resistor, and then here we've got a metal bar. And this is just resting on top. So it's resting on top, so they're all in contact, and it is a complete circuit. So the formula we get for that is this right here. EMF, or potential difference created, is B times L times V. So this is our EMF slash potential difference slash voltage. This is going to be our flux density, how strong the magnetic field is. L should be a script L. This is the length. And on here, let me just indicate what the length is. So this right here, this is our length of the bar. And then V is going to be the velocity. So how quickly this bar is moving off to the right is going to tell us how much EMF is produced. I'm going to do a quick derivation so this doesn't just seem like it's coming out of nowhere. So we have from before this formula here. Our EMF, this is Faraday's law of electromagnetic induction. EMF is the change. I'm going to ignore the n in this case here because it's only one loop. So it's the change in flux divided by the change in time. Now, flux can be listed as B times A. Now, the B isn't changing, so this is going to be B times delta A divided by delta T. Now, the area is the length times width. So if this is the length going from here to the bottom, then this is going to be the width. And we're not going to see this again because we'll see it'll just cancel out. So the area of a square, in this case a rectangle, is length times width. So I'm going to change this formula here to, this is going to be B. Now the length of the bar isn't going to change, but the width is. So I'm going to write it this way. So it's the magnetic field flux density multiplied by the length, multiplied by the change in width of the square, because we can see as it moves to the right, this width is going to be getting bigger and bigger and bigger of a rectangle. That's why our area is getting bigger. And we're going to divide this by the time. Well, what would we call this? How quickly it changes this width with respect to time? Well, the W over T, or the delta W over delta T, this is going to be our velocity. So delta W over delta T is velocity, and this leaves us with magnetic field strength, or flux density, multiplied by the length, multiplied by the velocity. So that's where this formula here comes from. Okay, so we'll try a few example problems later on, but just let's go through the energy transfers first. So when a force is applied, as in the above example, the bar does move a certain distance. So in other words, I'm applying a force on this bar and it's moving a certain distance, then we know that our work done is equal to our force multiplied by our distance. And so we are doing work. When we push this bar to the right, we are doing work. And in fact, what that energy gets transferred to is just electrical energy. So I've taken my own energy from my body, the chemical energy, converted that to kinetic energy in my muscles to push that bar to the right. As I push that bar to the right, I'm changing my mechanical energy to electrical energy, just like a generator does with a hydro power plant, for example. So that changes kinetic energy into electrical energy. And ultimately, this is going to go, or the waste energy is going to be as, sorry, as heat. So the resistor and the wires will get hotter. Now, here's the counterintuitive part. The conductor now has a current. So if we look in this direction here of this bar, what's going to be the direction of the current? Well, we can use, again, our right-hand rule. If the individual positive charge is here, so this positive charge here is moving to the right, the field strength is coming out of the page, so my index finger is to the right, my three fingers are pointing out of the page, so my thumb is going to be down. And that means that the overall current direction is going to be this direction through the loop, this direction through here. So it's going to produce this counterclockwise current. So, or sorry, clockwise current, I should say. So it's going down through this conductor here. Now, again, we know that a current carrying wire in a magnetic field produces a force. So what is going to be the magnitude and direction of the force on the bar due to the current? So pause the video here if you'd like. I want you to use the right-hand rule that tells us if the direction of the current in a current carrying wire with a magnetic field, what direction is that force going to be? So maybe you'll get it right away. If not, just pause the video to figure that out. Okay, well, hopefully you have figured it out. So I'm going to use my right-hand rule again for the current. My index finger is pointing downwards towards me, down to the bottom of the page. My three fingers are out of the page to indicate the direction of the magnetic field. And so what direction is my thumb going? Well, my thumb is going to be going in this direction here. And this is always going to be the case. So what you're going to find here is that using this formula, F equals B times I times L, plus using the rule, we're going to find the force is to the left. And more importantly, it opposes the direction of motion. Okay, so it's always going to oppose the direction of motion. One way of thinking about this, again, is tying it into the conservation of energy. If somehow, by pushing this bar to the right, I created a force which was to the right, you could see how you could generate an infinite amount of energy with a tiny amount of force. So I pushed it to the right, and then it gets faster and faster and faster and faster and faster with no energy input. It would be amazing. You could win some Nobel Prizes with that one. But unfortunately, that's not the way the world works, and you can't get free energy. So whenever you push a bar in a magnetic field, it's always going to produce a current which is going to oppose that motion. It's going to push back against you. So no free energy in this case here. We have three examples that we'll go through, and then So if you want to pause the video and try these practice questions here and come back when you're done with these three, and then we'll discuss the fourth one before the video is over as well. But we'll discuss that fourth one after we've done these three example problems. So go ahead and pause the video here and try and answer these questions. Okay, well, hopefully you had a chance to try these ones out. So let's take a look at this question here. A 25 centimeter rod, or I'm going to change that to 0.25 meter long rod, is moving perpendicular to magnetic field. This is the field strength. That's the speed. So this is a straightforward one. E equals EMF, epsilon equals B times L times V. This is going to be 0.20 times 0.25 times 1. That's going to be 0.05. So that's going to be the voltage that's produced, 0.05, or actually 0.05, zero sig figs there. Okay, example number 2. We have a 0.15 meter long rod moving at 2 meters per second, 3 Tesla field. If the resistance is 4 ohms, what is the magnitude of the current through the circuit? So this is just like one of these problems up here, or actually this question down here, very similar. So let's give this one a shot here as well. Well, we need to solve this in two parts. First one is finding out what the potential difference is going to be. And this is going to be 3 times 0.15 times 2.0. So 6 times 0.15, that's going to be 0.9. 0.90 volts. That's our EMF. And we also know that our V equals I times R, going back to our grade 11 physics. And so I equals V divided by R equals 0.90 divided by 4. And that's going to be 0.9 divided by 4. It's going to be 0.225. So this should be I equals 0.225 amps. Okay, and lastly, we have this question here. So 75 or 0.75 meter conducting rod, 8 meters per second in this direction here, and the resistance is 5 ohms in the circuit here. So yeah, so there we go. So this is moving to the right, it's closing off, it's decreasing the amount of flux in there. And so let's figure out the current. So let's go back to what we had before. Epsilon equals B LB equals 0.5 times 0.75 times 8. So that's 6 times a quarter is going to be 1.5. And if I take the current in the voltage divided by the resistance, that's going to be 1.5 divided by 5. It's going to be 0.3 amps. So there we go. We have 0.3, or should be 0.30 amps. Unless I made a mistake somewhere. Let me double check my work. So 0.75 times 8 is 6. Quarter of 6 is going to be 1.5. 1.5 divided by 5. Right here, 0.3. Yeah, okay, so that is correct. That's the current. Now what about the direction through X? So unfortunately, I've already got the answer key written on here. So regardless, either way, if we have this object moving to the right, we're going to have field coming out of the page. Then we're going to have, oh, you know what, maybe I did this diagram backwards. I apologize. I've kind of confused this question here. It should be maybe to the left. Okay, so forget this part about direction of the current here. You made a mistake with the drawing I've done on the question there. So ignore that part. Okay, now this last part here, I just want to show, essentially what I want to say is the direction and the magnitude of the EMF. So I'm not really too worried about the magnitude. What I'd like you to do for this question here is kind of draw a diagram of what's happening with here. Just go into a little bit more detail. Okay, so let's say I have a graph of the EMF produced and the distance that it's going through. Now, the reason why I have this question here is I want to tie together the idea of Lenz's law plus what we've learned today about a conductor moving in a magnetic field. So what I'm going to do is I'm going to think about just this bar here as it moves into the magnetic field. Now you'll notice this bar is in the magnetic field, but this bar over here is not in the magnetic field. So for this bar here, this is moving to the right. So if we imagine one of the positive charges here moving to the right, the field is into the page. Well, what direction is the force on that positive particle going to be? So pause the video if you need to here and think about what that means for the direction of the EMF or the direction of the force on the positive charges. So if you've paused the video and now you're back, hopefully you'll recognize that for this part here, if my index finger and my right hand represents the direction of that positive particle, my three fingers are going to go downwards into the page, and my thumb is pointing towards the top of the page. So that means that this positive charge is going to experience a force going upwards, which is sort of like saying that we've attached a cell to this part here. So a cell produces an EMF going in this direction. So this part of the beam right here is producing an EMF where the positive voltage is at the top. So it's trying to get more positive charges at the top and push more negative charges towards the bottom. So this is going to produce an EMF which is moving in the counterclockwise direction. So I'm going to call this a negative EMF or counterclockwise. So as long as this bar is in the field and this bar is not in the field, we know we're going to have an EMF that's going to be counterclockwise, which I'm calling negative here. Now in this second position here, the EMF is going to be produced from both bars. So both of these bars now are in the magnetic field. So if we look at this bar here, just as before, right-hand rule, positive charge moving to the right, field into the page, this is going to produce an EMF going this way. But if we look at this bar here, there's also going to be an EMF being produced the same way. The bar is going to follow the same rules. A positive charge in here is going to move into the right, field into the page, my thumb points upwards. So what's going to be the overall EMF in a loop like this? Well, hopefully you'll recognize that this is going to be zero EMF overall. It may be slightly more positive at the top of the loop, maybe slightly less positive at the bottom of the loop, but overall there won't be a current being produced. You essentially have two cells or two batteries that are opposed to each other, so the overall EMF will be zero. Now, lastly, in this scenario here, hopefully you're recognizing the pattern. This bar is still in the EMF, so it's producing a or still in the magnetic field, so EMF is going upwards here, but this one is not in the EMF or not in the magnetic field, so no EMF. So overall, we're going to have a EMF going clockwise or a current being produced clockwise as well. So I'm going to call this a positive EMF. I want to draw your attention to the comparison, like I said a moment ago, about these two rules. So none of these, like Lenz's law and this idea of EMF equals BLV, none of these are fundamental physics of principles of physics. These are all essentially ways of interpreting fundamental law of conservation of energy for reasons that are a bit complex to discuss in a short video, but some of it you can hopefully kind of intuit here. So these are essentially the inevitable repercussions of the conservation of energy. You can look at this loop here and use Lenz's law, and the exact same thing, exact same results will come out from it. So for example, if I use Lenz's law for this first diagram on the left hand here, what's happening in terms of flux in the loop? Well, as this loop moves further and further to the right, there's going to be more and more flux going through the loop downwards. So Faraday's law or Lenz's law says that we need to produce a current which produces a flux which cancels that. So if I have more and more flux going into the loop, well then I need to get more and more flux going out of the loop to cancel that, or going out of the page. And so that would mean that if I use my right hand rule, I need to produce some upward flux to counteract the new downward flux going in there. So my fingers are going to curl to the left, and so lo and behold, we'll find that we have a counterclockwise current being produced in the loop. Now, as it's moving through the middle section here, well, what's happening to the amount of flux going through the loop? Well, what you'll find is that as it moves to the right, the total amount of flux going through the loop isn't going to change. If this flux density is constant, then the amount of flux is going to stay a constant. As we move to the right, we have less flux over here, but we have more flux over here, and so it's going to, as long as it's in the middle here, it's going to cancel out. And so Lenz's law would say if there's no change in flux, there's going to be no induced current, which is again what we found here. Now, as we move to the right, we're going to get less and less downward flux, and Lenz's law says we need to counteract that, so we need to get more and more downward flux. Well, how do we get more downward flux? Well, our right-hand curl rule tells us if we want more flux into the page, and we point our thumb downwards, our fingers produce a clockwise current there. So Lenz's law will tell us how to solve this question. This rule of epsilon equals B times L times V, that's also going to give us the same information. Ultimately, these are just ways of representing the conservation of energy, but there's two different ways to solve these problems. So that is our last video for the year in terms of this content. So hope you've enjoyed it. If you have any questions, feel free to come by FitBlock. And most importantly, yeah, enjoy the rest of the year. Thank you.